Dear students, today we will try to understand Fermi Dirac Statistics. We know this is also called FD statistics. FD statistics. Okay. So the particles are basically particles which obey this are basically indistinguishable. And only one particle occupies a given energy level. The one more point regarding this statistics is that particles obeying this FT statistics, they have basically half integral spin. The examples for this case may be protons, simply electrons, helium-3, or you can write it as, that means the helium having mass number 3. One more is nitric oxide. Okay, nitric oxide is also having half integral spin. And the particles obeying this statistics are basically called as fermions. Now we will see it is derivation part. Suppose if we consider that the Ni particles they are distributed among suppose Gi states, you can say among Gi states, and the condition here is the Gi states are basically greater than this Ni particles. What is Gi? We already know it is simply the degeneracy of ith state, or you can say ith energy level. Now imagine that first we will take a case where the particles are distinguishable. First we will take a case where particles are distinguishable. So this basically implies that the first particle may be placed in one of the GI states. That means the first particle can be placed any of the GI states first, and second particle that may be placed GI minus 1 state. Third particle that may be placed in GI minus 3. And similarly we can say the Ni particle can be placed in GI minus Ni states. Why? It is very simple. So the number of arrangements when we consider a system in which the particles are, we have to remember, very important, distinguishable, then the number of arrangements is simply given by Gi factorial upon Gi minus Ni factorial. Now, but this statistics basically involves particles which are indistinguishable. So if the particles are indistinguishable, this expression then has to be divided by the number of permutations of Ni particles, which will be basically equal to Ni factorial. That means this equation will turn out to be, or you can say the number of arrangements will be equal to, for this indistinguishable case, will be equal to Gi factorial upon Ni factorial Gi minus Ni factorial. We can understand this Gi minus Ni with a very simple case. Suppose if we consider these as energy states or cells, and we have particles, suppose particle number 1, 2, 3, 4, 5, 6 and so on. This first particle at the first instance can go in any of the states, that means Gi. Now the second particle can go into this cell or this cell or this cell, because suppose we will consider the first cell is now occupied with the first particle. Similarly the third particle go into this, that means Gi minus 2, and similarly that is why we get here Gi minus Ni status. Now we will see the thermodynamic probability, which is basically given by W will be directly proportional to product of these arrangements, that means Gi factorial upon Ni factorial into Gi minus Ni factorial. Now to remove this proportionality we will simply add a proportionality constant. So it will be equal to pi I gi factorial upon ni factorial gi minus ni factorial simply multiplied by a constant. Suppose this is our equation number 1. Now we will take the logarithm on both sides, taking logarithm on both sides, we will simply get a relation ln of w will be equal to, when you take the logarithm, this product changes into summation. Okay, and it will be log m upon log n, which will be equal to ln of gi factorial, and log m upon log n will be log m minus log n, that means minus log of ni factorial minus, we have taken the natural log, so you can take log or natural log. So here we have taken the natural log, we will write it as ln, or ln of gi minus ni factorial, and this will be changed into the plus constant. So now we assume here that this ni, gi and gi minus ni are basically very large. So we can simply applying Stirling approximation. Stirling approximation. So if we apply Stirling approximation to this equation number 2, you can say, suppose this is equation number 2, we will get this equation then, that means ln of w will be equal to, summation will remain as such, it will be gi ln of gi minus gi. So this is for this case Stirling approximation. Similarly we have minus, we will write it as minus ni ln of ni minus ni, it would have been, but minus is already outside, so it will be plus ni. Similarly for this case it will be minus gi minus ni ln of gi minus ni, but plus gi minus ni plus constant. So we will get this relation. Now we will further simplify this relation. That means we will get ln of w will be equal to, the ni and gi will cancel out, in the previous relation, so we will get Ni, and if we take minus inside, and minus minus will be plus, and we will write first this term Ni minus Gi ln of, it will be same Gi minus Ni. You have to remember this point, it is Ni minus Gi, not Gi minus Ni. Okay. Then minus Ni ln of Ni plus Gi ln of Gi plus constant. So we will get this relation. So suppose this is equation number 3rd. Now the most probable state, can be simply found by making the W as maximum and making it as differential equal to 0. So that means if we differentiate this term, that means differential of ln of W will be simply equal to 0, because first derivative, if we make that equal to 0, that means we are actually maximizing a function. So we will write summation of I, and differentiating this with respect to Ni, it will be equal to 1. This is with respect to Ni, it will be equal to 0, so it will remain as such. Similarly for this case, and this will also be equal to 0, this term. So we will get this ln of Ni minus ln of Gi minus Ni, only these two terms, and we are basically differentiating it with respect to Ni. So, and we are maximizing it, so it is first differential, that means this will be equal to 0, so we will write it here. Or we can say this relation can also be written as, because this is equal to log of m minus log of n, so it will be simply equal to ln of m by n, that means Gi minus Ni, and it is with respect to the Ni particles, it will be equal to 0. Suppose this is equation number 4. We have also taken into consideration that the total number of particles is basically the summation of Ni particles, which is constant, and if we differentiate a constant, then it will be equal to 0. So delta n will be equal to summation I delta Ni will be equal to 0. Similarly, if we take total energy, you can write it U or E, it will be equal to summation I Ni Ei. This will be also constant, and if you differentiate this relation, it will also be equal to summation I Ei delta Ni will be equal to 0. Now applying Lagrange's method of undetermined multipliers. We have basically got this equation number 4. What we will simply add these multipliers, that means alpha and beta, what we are actually doing in the doing to these equations in previous lectures also. So we will get summation I ln of ni upon gi, the equation number 4, plus alpha plus beta and ei energy, right? And it is with respect to ni, it will be equal to 0. Now we know, since the variation of this delta ni are basically independent to one another, so it cannot be 0, hence it is coefficient this much, this will be equal to 0. So we can write, it implies that ln of ni upon gi minus ni plus alpha plus beta ei will be equal to 0. Or we can write this relation as ln of ni upon gi minus ni will be equal to minus alpha minus beta ei. So if we take the reciprocal of this, it will be equal to ln of gi minus ni upon ni, but it will be now negative, will be, if we take the negative outside of both the terms, it will be alpha plus beta ei. So simply this negative and negative will cancel out, so we will get this relation. That means now ln of gi, or we can write it as, if we give back both to these terms ni, right, it is gi upon ni minus ni upon ni will be equal to alpha plus beta ei. So you know ni, it will be 1, so we will write it as gi upon ni minus 1 will be equal to alpha plus beta ei. If we multiply both the terms with the exponential, here exponential and exponential, this ln and exponential will go, this will remain as gi upon ni minus 1 will be equal to e raised power alpha plus beta ei. Or we can write this relation in terms of ni now. So that means we can write it as, if we take first this minus 1 to here, it will be then the plus 1, or that means we can simply write a simple relation which is ni will be equal to gi upon e raised power alpha plus beta ei plus 1. So this is the basically the required equation which relates the most probable distribution of n particles among the energy levels according to Fermi Dirac. Okay, thank you.